Awesome. Thank you very much. So I'm also sorry that I can't be there in person. Um, uh, Moving me from Cardiff to California and back again at short notice didn't seem like a reasonable use of resources, given that I would only be able to be there for the duration of my talk. So yeah, this talk is about the Simons Observatory in general. And because of that and the short notice of the talk, it is going to be very much from the perspective of describing the Simons Observatory to you at a relatively high level, but hopefully I'm still going to be able to say some interesting things for you in terms of telling you what the Simons Observatory is in general, if it's not something that you're super aware of before. So updates on how it has been progressing, because there's been a lot of things happening on the ground in Chile over the past few months, and the Simons Observatory is really progressing at quite a significant rate now. And then also taking you through some of the approved science forecasts that have been made for the Simons Observatory to give you an idea of how good the data is going to be from the Simons Observatory and focus on some of the relevant parts of the data for constraining dark matter physics. And then at the end, I will also talk a bit about one of my main focuses within the Simons Observatory, which is working on the likelihood analysis tools, which we are building for analyzing all of this data, and talking about how we want to be able to be open in our interactions with the community on building those analysis tools. So the Simons Observatory, in a nutshell, is a cosmic microwave background experiment. It's located in Chile, and it comes in these two main parts. So there will be 3 SATs, or small aperture telescopes, which appear on the right-hand side of this image here in their 3-meter high, I think, ground baffles on the right, with half-meter mirrors. And there is one large aperture telescope, or LAT, which has a 6-meter mirror and has this rather larger ground structure over here. That's what is currently on the ground in Chile and is at various stages of commissioning. There will also be arriving as part of the Simons Observatory 3 more small aperture telescopes, which are being contributed by the UK and Japan. And there will be extra optics tubes, which will go in the existing LAT receiver. There are currently 7 which are on the ground in Chile. There will be 6 more coming as part of the approved advanced SO program. And there will be 1 extra one, which uses a slightly different type of detector, or a KIDS type of detector, which will be coming from the UK in the future. And overall, once all this exists, in 3 or 4 years' time, there will be a total of 60,000 new microwave detectors pointing at the sky and looking at these CMB signals. The 2 different types of telescope focus broadly on 2 different types of survey and 2 broadly different types of observable. So the SATs exist primarily to look for primordial gravitational waves in the form of B-mode polarization of the cosmic microwave background. The 3 SATs will be looking at mainly a southern patch of the sky down here in a region which is lower in dust foregrounds than a lot of the rest of the sky. And the large aperture telescope focuses on smaller scale, by which I mean smaller angular scale, higher resolution in the CMB, but over a much larger area of the sky. And the reason for the existence of the SAT and its much larger mirror is to get the delensing for being able to measure the primordial B modes as well as possible from the SATs, but also to do the large area CMB science in cross correlation with other experiments in terms of lensing, as well as getting the primary CMB really good in polarization and on small angular scales. So this LAT survey will be over a fraction of about 40% of the sky, covering most of the southern region, with significant overlaps with a lot of large-scale structure surveys like DESI, the existing DES, which are the ones foregrounded on here, and then also LSST and Euclid as well. The sensitivities and different frequency bands of the two different telescopes are just shown here. Each of them has a significant number of frequency bands in order to help with disentangling the microwave foregrounds, which are otherwise shrouding the CMB beyond, but also to help us see some of those CMB secondaries, which exist as foregrounds for the primary CMB, but can do good cross-correlation science with the large-scale structure data. This is the kind of data and data quality that we will be getting from the Simons Observatory. So on the left here is just a summary of the primary CMB observables. So this is the CMB temperature angular power spectrum, which is shown as the highest one on here. And then the E mode angular power spectrum is the middle one, and the B mode is the lower one, where this is a synthetic signal of R is 0.01 for the dashed line for the B modes, of course, meanwhile it's at the Planck cosmology for the other ones. But the point is that you can see that for Simons Observatory, which is the blue points and error bars here forecasted, we are able to go to significantly higher angular resolution than Planck, whilst still maintaining also sensitivity on large scales, which helps us both in temperature and polarization. And of course, this primordial B mode signal, if it exists, is going to be great to detect with the SATs. Another observable that we will be able to measure with the Simons Observatory is, of course, the lensing. And Alex has just done an excellent introduction as to why lensing is an excellent probe of dark matter and dark matter structure formation over the history of the universe. Of course, here we will not be using the shapes of galaxies as our tracer for the matter potential. We will instead be using the CMB temperature and polarization fluctuations, which exist at a redshift of 1100, so sensitive to the integrated matter all along the line of sight out to that redshift and that very well-known redshift. And for the Simons Observatory, the contentful point is that we will increase the signal to noise and the measurement of the CMB lensing from current experiments. So here I've given Planck, but it's similar for ACT and SPT, from an SNR of about 40 to an SNR of about 140. In terms of where we are right now with the Simons Observatory, the quote is that construction is well underway. What that means is that the 3 SATs are basically complete. There has been first light on 2 of the 3 SATs, the 2 mid-frequency SAT telescopes, which happened last autumn, and Simons Observatory is officially entering the operations era, is the phrasing which has been used. The large aperture telescope, the receivers and the telescope structure are on site, and there have been dark field tests which have gone very well. The mirror is not arrived in Chile yet, but is scheduled to do so for the operations of the large aperture telescope to arrive in 2025. And then from then, the full science operations will run until 2029, at least for the initial Simons Observatory operations phase. So here you can just see on the bottom left a couple of maps which have been made from the SATs, one of Jupiter, one of the Moon, and then this is just some dashboard data for doing operations that people have been very excited to start seeing data stream into. This I do not expect you, of course, to read, but it just gives you an idea of what the timetable is for SAT and LAT commissioning and deployment. And basically, it starts from the point in the middle here, which is May 2024, where the SATs come online, which are these green boxes along the bottom part, which should be hopefully fully commissioned and ready to go by the latter part of this year. So August 2024 is this point. You can see my cursor on screen. And then the orange boxes are referring to the large aperture telescope with the mirror arriving, and then full commissioning for the full SO operations to start towards the end of this year and into 2025. Okay, so that's where we are and what we are building with the Simons Observatory. So I'll now go through some of the science goals and forecasts, which were officially stated in this document from 2018 and remains the reference for our official sensitivity and forecast levels, picking out in particular 3 main focus areas, which are, of course, hopefully relevant for this workshop and a dark matter focused audience. So one of which is the sensitivity of the CMB lensing signal to probe the mass distribution at quote unquote late times in similar ways to the talk Alex has just been giving about galaxy weak lensing. The other of which is the sensitivity of the damping tail of the CMB temperature and polarization to energy injections and dark matter and baryonic interactions. And then also something else which was touched on in the questions and at the end of Alex's talk, which is the ability of the Simons Observatory to measure the gas in the galaxy clusters through the Sun-Yau-Zeldovich effect. Also combine that with the lensing constraints on the galaxy cluster mass profiles and use that to, again, learn about these potential suppressions, for instance, of the dark matter power spectrum, as well as doing things like cluster number counts and the cosmology that you can do in that way. So for lensing of the CMB, as I said, it is a probe which, rather than using the galaxies at photometric redshift bins up to redshift 1 or 2, uses a very specific spectroscopic signal at redshift of 1100 in order to measure the projected matter density along the line of sight. We use the non-Gaussianity of the CMB in a very particular way to measure that CMB lensing signal and can get good sensitivity to the matter power spectrum, particularly on linear and quasi-nonlinear scales, which are smaller typical physical scales than is probed by the primary CMB, but larger physical scales than is probed by galaxy probes like galaxy weak lensing. So here, these are not Simons Observatory forecasts. They are some measurements in current data for a particular dark matter interaction model from this paper, but this is just showing you the sensitivity of this lensing power spectrum observable to the interaction strength and also relative the way that it is suppressed in the matter power spectrum. Alex has already shown this plot, which is becoming a very commonly shown and influential plot because it very succinctly summarizes exactly the interesting point Alex was making about the origin of potential tensions in S8 and whether that is pointing us to an explanation for dark matter in terms of scale and redshift dependence of this suppression of the matter power spectrum. And of course, Alex drew your attention to the weak lensing box, which probes a large variety of linear and nonlinear scales at low redshifts. The CMB lensing box, which I will also draw your attention to, is up here because, of course, the lensing kernel extends out to a redshift, a high redshift, but picks up contributions all the way down to lower redshifts. And I would also point out that CMB lensing cross-correlation boxes, which I will mention more in a moment, which are capable of probing more intermediate regimes in terms of both the redshifts and the angular scales from doing lensing cross-correlations of CMB lensing and galaxies. By doing that, we can also exploit the tomography, which you can do using galaxy samples in order to track this potential suppression as a function of redshift and or scale in order to disentangle potential explanations for it, be they dark matter models or baryonic interactions. And again, this is the forecast from the Simons Observatory for how well we will be able to do this. Particularly here, it's a 3x2 between the CMB lensing and the galaxy clustering from LSST, and the different redshift bins which we hope to be able to do that in. And then again, just to illustrate how this signal appears in terms of sigma 8 as a function of redshift for a particularly chosen interacting dark matter model with different assumptions for the parameters. And you can see how being able to track this as a function of redshift will be very helpful. Another thing which is of interest from the Simons Observatory for galaxy weak lensing is the ability to use this extra lensing bin at very high and very well-known redshift to calibrate some of the lensing nuisance parameters, which are otherwise have to be modeled and marginalized over in galaxy weak lensing surveys or in galaxy clustering. And this is both useful for things like weak lensing shear calibration, and this shows cross correlations in the diagram on the right here, meeting the LSST requirements for the knowledge on that calibration for LSST samples. Something that I've worked on a lot in the past is doing cosmology with radio galaxy samples as well. And I would just point out that those radio galaxy samples typically do not have well-constrained redshift distributions. And one can also think about constraining the redshift distributions of sources using this extra CMB lensing bin, and then using that to then help you with any subsequent science you want to do with the radio sources. The primary CMB is also very useful for looking at non-gravitational dark matter interactions, be it that through the damping tail, high angular resolutions, the peak smearing, or also changing the background evolution and seeing how you can combine with things like BAO. So here, again, these plots on the bottom left are not SO plots, but they show an illustrative example for the expected change as the different colored lines in the TT and EE primary CMB power spectrum for a particular dark matter model. And then here you can see the Planck data in black overplotted with the error bars. And then I have just suggestively indicated to you how useful the extra high resolution higher L data points will be from the Simons Observatory in constraining these kinds of models. The forecasts which are given specifically within the Simons Observatory forecasts are for dark matter proton elastic scattering with these two different potential dark matter masses, GeV and MEV, and the upshot is that these will be about 8 times better constraints than Planck. The other very interesting potential dark matter model that people think about with a lot of these observables is ultralight axions. And this is the official forecast for how much better these combined SO probes will be at constraining the axion dark matter fraction as a function of the axion mass. I also mentioned cluster number counts. So the Simons Observatory will be great at finding galaxy clusters through the SC effect. We expect to see about 16,000 of those. We expect to be able to do lensing mass calibration to a factor of about 3% on a stack in a particular mass bin, and also be able to use that to then track this evolution of the clustering amplitude parameter as a function of redshift, using specifically just those clusters, and then also use this extra angular resolution and sensitivity to do great things for constraining cluster mass profiles, be that splashback radii or using in combination with weak lensing in ways that Alex was also describing earlier.
Ian, so, time. Slowly wrap up, please.
Yep, no problem. So I'm on my last couple of slides. So we want to be doing full multi-probe analyses with the Simons Observatory across the primary CMB, the lensing, the clusters, and also the external large-scale structure data sets, and folding all of that together in a coherent and combined analyses to try and do things as simultaneously as possible for obvious reasons, maximize our statistics and minimize our systematics. I am in charge of developing this likelihood and theory code for doing this within the Simons Observatory, and we are rolling that out on existing data, including this recent ACT Cross DES paper, which I was involved in. We are also very much exploring how well we can do with accelerating our inference pipelines by using emulators for Einstein-Boltzmann codes. And I would draw your attention to the paper which came out last week or the week before last now, from Hidde Jenser, who is a PhD student in Cardiff, where in particular we focus on how to validate and package Einstein-Boltzmann emulators for reuse. So this is about trying to create standards which allow people to use and reuse Einstein-Boltzmann emulators across different types of analysis code. And then we're also interested in the cross-probe covariances. So we're not just doing a simple combination of the data vectors, but we're actually taking into account the covariances fully. Along with all things in the Simons Observatory, those things I've just mentioned are being done in as open a way as possible, in terms of not only just putting code that ran for us once on GitHub, but also trying to ensure that that code is well tested, has a full test suite on multiple different platforms, and is actively maintained in order to be able to help the Simons Observatory be as of much use to the community for testing interesting models as possible. And based on that, I would also point you to this CMB analysis school, which will be taking place in Chicago in the middle of July, immediately before, but not completely related to the Simons Observatory collaboration meeting. And if you're interested in learning how to do and use CMB data for constraining models, that will be a great place to go. It's building on the legacy. Hopefully some of you have already used some of these ACT collaboration notebooks, but I would point you to those as well as being very interesting. So I will also just say Simons Observatory can do other things. There's a great galactic science effort. Simons Observatory will do great things for transients in the submillimeter regime, which is something people often don't think about, and also will be one of the first things to look at reionization constraints in kinds of the KSE contribution to the power spectrum, which may also be of interest to you too. So these are my conclusions. Thank you very much.
All right, thank you.